confidence interval for proportion using the Z table. In a random sample of n equal 100 patients, the proportion cured by a new drug, p hat, 60 over 100 or 0.6. This is taken from a larger population, the population of millions of patients. The proportion that would be cured by the new drug in the long run is represented by p, and that's unknown. Part A, we want 90% confidence interval for the proportion of patients that would be cured by a new drug in the long run. So Q would be the portion that are, Q hat would be the portion that are not cured in our sample, and that's would be 1 minus p hat, or 1 minus 0.6 or 0.4. And in order to computing the exact probabilities using a binomial distribution would be very time consuming. So we hope to apply the central limit theorem and use the Z table. So in order to do that, we need to check that n times p hat and n times q hat are both at least 5. So n times p hat, 100 times 0.6 is 60, that's more than 5. N times q hat, that's 100 times 0.4, that's 40, that's more than 5. So they're both yeses. So that means we can use the Z table, and we don't have to compute the exact binomial probabilities. Okay, so our desired confidence level is 0.9. That's represented by 1 minus alpha. So alpha itself is our level of doubt. That'd be 1 minus 0.9, which is 0.1. And then half the doubt is 0.05. So we want to place half of our doubt on each extreme. We'll have a two-sided confidence interval. And then our table is based on only the upper half. So we're not going to look up 0.90 in the table. We're going to take half of that, 1 minus alpha divided by 2 is 0.4500, and look that up in the Z table using the table in reverse. And it's in the closest numbers are in row 1.6. It's not there exactly. The closest numbers in row 1.6, columns 4 and 5. So it's actually about halfway between the two probabilities in those two columns. So we can estimate that the Z score is going to be halfway between 1.64 and 1.65 or 1.645. The next step, we want to plug into this formula to create the lower bound and upper bound for the confidence level. These two formulas are the same except for the sign in the middle. So it's p hat, which is 0.6, minus z, which is the number from the table, which is 1.645, times p hat, which is 0.6, times q hat, which is 0.4, divided by the sample size, and 100. And I'm going to compute what comes after the minus sign first, because sometimes that is reported separately. 1.645 times the square root of 0.6 times 0.4 over 100 comes out to be 0.08 something. And that's called the margin of error. And if we subtract, we get approximately 0.52. It's our lower bound. The upper bound is the same, except we want to add the margin of error, and that comes out to be about 0.68. So that means we are 90% confident that the proportion cured by the new drug in the long run would be between 0.52 and 0.68. In part B, the margin of error, as we saw above, that was approximately 0.08. Example 2. A lot of times it's good to know in advance how large your sample should be. If the sample is too small, you may not get the results that you want. If the sample is too big, you may get you'll get the results that you wanted, but you may end up spending more money than you wanted to spend because large samples can be expensive. In this example, pollsters wish to determine with 90% confidence the proportion of voters who support Biden for president with a margin of error of less than 0.03. And how large should the sample size be? our confidence level 1 minus alpha is 0.9, and we want our doubt is going to be 1 minus 0.9, which is 0.1, and then we want half of our doubt on each extreme, so alpha over 2, 0.05. Our table only has the z-score probabilities between 0 and the upper critical value. So we need to divide the 0.90 by 2, it's 0.45, and look that up in the table. And we already computed that in example 1. That's it was not in the table exactly, but we estimated it to be 1.645. Since we don't know the proportions, sample proportions in advance, we're going to estimate p hat to be 0.5 and q hat to be 0.5. That'll give us a little bit of an overestimate, if anything. It's better to be probably better to overestimate the number of your sample size rather than underestimate, and by making p hat and q hat both equal to 0.5, if anything, it'll give us an overestimate. And then we can plug into this formula, p hat times q hat times the number from the z-table divided by our desired margin of error. So it's 0.5 times 0.5 times 1.645 divided by 0.03, and that fraction squared. It comes out to be 751.67 some voters. It's not going to be feasible to sample a fraction of voters. If we round down, that's going to it's going to put our margin of error over 0.03, which is more than what we wanted. So we need to round up. Even if it was 0.01 after the decimal point, we still need to round up. So we round up to 752 voters. And that concludes this presentation.